So I'm Professor Roland Fleck. I'm Academic Director of the Centre for Ultrastructural Imaging at King's College London. So King's College London's a Russell Group university located in London, United Kingdom. It's a major teaching and research centre with an international reputation. We cover everything from medical and the life sciences through to chemistry, physical sciences, and the arts. And the Centre for Ultrastructural Imaging, of which I'm academic director, is its core electron microscopy facility here to help support the broadest range of research and academic adventure as possible. So my personal interest in research is really focused on instrument development and innovation. That's really to allow the facility, Centre for Ultrastructural Imaging, to progress and remain current. The major challenges we've encountered is really relating to charging artifacts, sample stability. Our preferences to work with vitrified cryo-fixed material, which is essentially frozen. It's extremely beam sensitive. If you put too much dose in, you will devitrify your sample. It doesn't have any introduced contrasting mechanisms. We don't use heavy metals. So as a result, it's a challenging sample to work with. And that's why we've been approaching SenseAI to try and resolve some of our technical challenges. In terms of cryo-electron microscopy, it probably depends upon your starting position or your perspective. In transmission electron microscopy, the cryo approaches are fairly well established, particularly for structural biology. The Nobel Prize was awarded in 2017 to Richard Henderson, Jacques Dubochet, and Joachim Frank. So in that field, it's considered essentially an essential tool and is fairly well adopted across the research community. In the large volume imaging community, cryo is still really in its infancy. The majority of groups would use chemically fixed, resin infiltrated, and heavy metal contrasted samples, and they would be looking to use serial block phase, so essentially a microtome located inside the SEM chamber to section and then image repeatedly over an extended period of time, or fib milling, where essentially you use an ion beam or a plasma beam to sputter away or remove your top surface and then image, or an array tomography approach, where essentially you would do all your sectioning external to the microscope, load a large number of individual sections, and then image them sequentially. But all of these are based upon the room temperature resin infiltration approaches. The challenge with all of these, albeit them extremely stable once you get into the microscope, is they are sensitive to processing artifacts, particularly changes in your lipid membranes can be disrupted by the chemical fixation approaches. They are subjected to quite severe osmotic stresses during the processing, which can change the shape of organelles. You disrupt some of the organelle structure and organization, and soluble components can be displaced, moved, or lost from the cells. Essentially, you are trying to interpret the image based upon what you've done to the cell in preparing it for the electron microscope, which is unlike cryo. In the cryo techniques, we rely on vitrification, so very, very rapid cooling of the cells to essentially move water from its liquid state to a metastable state without the formation of ice crystals. And essentially that preserves the cell in its living native state. All the membranes are essentially preserved without further osmotic stress, so they should be as close to how they were in a living state as humanly possible. So one of the major challenges for VEM, volume electron microscopy, which is really a rapidly developing field, is the size of the volume which people wish to achieve. Essentially, the bigger the volume, the more informative it is. Essentially, because you're wanting to look at all of the cellular components and perhaps even multicellular environments, so you can understand how each individual cellular organelle or structure relates to its neighbor or associating organelle, and how each individual cell, and cells come in all different flavors, sizes, shapes, and types, how they all interact together to form a functioning tissue. So this is really where volume electron microscopy is extremely innovative and valuable to understand these larger interconnecting relationships between cells and organelle. Obviously, the bigger the volume, the larger the data set, which makes processing extremely challenging. And in addition to that, the larger the volume you wish to acquire, the longer it takes. So we have a challenge in terms of total data volume and the time required to acquire the volume, which in itself puts a pressure on the microscope because it has to remain stable, functional, and operational for very long periods of time. And this could be measured in weeks in many cases. So SenseAI has two advantages in this area. One, the compressive sensing approach essentially acquires smaller data volumes, which helps with the post-processing of data. But one of its major advantages is if I'm only collecting, say, 20 or 25% of the field of view by using the compressive sensing strategy, I'm essentially working 4 or 5 times faster than I can otherwise. So the time required to complete an entire volume is significantly reduced, which is less stressful on the instrument, less stressful on the operator, and generates much higher success rates. So one of the other challenges I have, particularly with focused ion beam scanning electron microscopy, the same would apply to plasma sourced instruments, is that the milling material is essentially being used each time we turn on the instrument and we're milling away a surface. That comes with a significant financial cost. If I can acquire the same volume in a quarter or a fifth of the time, my source lasts 4 to 5 times longer. So it's quite a significant difference in terms of the total cost to generate a single volume, which is an added advantage of using the SenseAI approach. I think volume EM has been developing extremely rapidly over the past maybe 5 to 10 years, certainly the last 5 years, and it's become incredibly valuable as a basic tool in life science research, notwithstanding the challenges of sample preparation and artifacts being introduced. If cryo volume imaging can be made robust and routine, and certainly the instrumentation, which I have, is extremely robust, with the aid of SenseAI to help with signal to noise, damaging artifacts, charge balancing, and speeding up the entire process, you could envisage a situation where cryovolume EM becomes routinely practical and simple to apply within a laboratory environment. If that's the case, then I could see wider adoption and more labs employing it. Certainly, high pressure freezing to vitrify your sample or plunge freezing to vitrify cells on grids is routine and very well established. Cryosample transfer can be conducted cleanly and robustly if your laboratory is sufficiently well equipped. The FIB systems are also extremely stable and well engineered today. Really, the challenge is handling the vitrified sample and the difficulty of actually imaging it and generating sufficient signal to noise to allow you to reconstruct your volume and analyze it in a meaningful way. And SenseAI is essentially opening that door to us at the present moment in time. Well, in principle, the SenseAI approach, where I can simply use it to speed up the process and manage the imaging part of the data volume generated at the end of a volume acquisition, makes it applicable to any scanning modality, which would apply equally as well to room temperature FIB-SEM, serial block phase, or array tomography if you're using the SEM to collect the data. It also has large numbers of opportunities in STEM, which can also be employed in a cryogenic environment. So I think as a broader tool, if it's easily accessible to the end user and perhaps somebody who's not a computational expert, it opens up the avenues for the compressive sensing and SenseAI to be essentially routinely employed as a acquisition tool on any microscope that's suitably equipped.